can start. Okay, good morning and welcome back. Right, now we are moving into more of a generic, the remaining 3 lectures, if you have seen the schedule. We are now talking about application of remote sensing products. Then we have 2 lectures, one on climate and eco-hydrology, and another one is sustainability and eco-hydrology. Right, and that's with that we will be mostly wrapping up the theoretical part of it. Okay, how many of you have used remote sensing products? All of you have used. The DEM was remote sensing product, right? That you have started to set up the model. Yes? How did we get that DEM? We use GIS. We use some products. Anyone thought about how the DEM has come? Or how do you generate a DEM? Let's say someone asks you that you have to generate a DEM. How do you do that? Satellite? Sensors? What happens in these satellites or sensors? Okay. Basically, any remote sensing products uses the electromagnetic radiation and how the surface reflects it back. Based on those reflective characteristics or properties, you try to estimate what is required. So DEM is something similar, right? Before the satellite products also DEM was there. How do we generate that? Manual survey. You do a manual survey. Your topo sheets are form of your DEM. Yes, you have the contour lines on that. They were generated much before even the remote sensing products were available. Okay. So your remote sensing as such, there are 2 ways of doing it. One is what we call as active remote sensing, another one is passive remote sensing. What is the difference? Source of energy. In the passive, what is the source of energy? Solar radiation. In the active, it itself will send out a radiation and it will try to see how is it coming back. Okay. So let's see how these remote sensing products can be useful for our eco-hydrological modeling. A lot of literature is there, a lot of work is going on. We are using it already for the application of SWAT model, or what you say, for setting up SWAT model. But in addition to that, can we use some of these biophysical parameters in our SWAT model to improve it, right? That's what we start work with. So coming back to the lecture outcomes, you will have an overview of remote sensing products for eco-hydrological variables. We have a list. We'll be able to utilize the indices that show vegetation-water interactions. Some of the indices you might already be knowing. Have a conceptual understanding on process of integration of remote sensing data in eco-hydrological modeling. Okay. Now, this is a watershed. Okay. It has 2 gauge points. And mostly we use the stream flow data from these gauge points to evaluate a watershed model. Now, anyone knows what is the principle behind it? Why do we use this stream flow data? Or what is the hypothesis here? When you compare a model with a point measurement, obviously which has a spatial representation, what is the hypothesis here? My question is, how valid is comparison of a hydrology from a hydrological perspective with a point based measurement? Yield of the catchment. Okay.
While calculating the whole watershed area, we have to find out the upper points, the higher points, and from that point, the whole water stream and also originated. And the point where we measure it, so it is
measurement may happen. Yes, it's correct. So this point, the measurement is basically the response of this entire catchment to some inputs. The hypothesis is whatever is the catchment response can be observed to stream flow, right? In that process, any changes in your catchment or in your system will get reflected in your stream flow. And other aspect of it, measuring stream flow is relatively more easier than measuring other ecohydrological variables, right? One is because of the spatial variation, and also you cannot have point measurements. Evapotranspiration will have a spatial variation. Soil moisture will have a spatial variation, right? Crop growth will be varying from one part of the watershed to another part of the watershed. So there is a spatial variation that is occurring, and it becomes challenging for us to measure all the variables. And that's where the remote sensing products do help us. Remote sensing products have the ability to capture at a various spatial resolution, right? So although we compare here, we are also realizing that even though this is matching, this might be matching, you're observed and simulated. When you're modeling, it might be matching. It is possible that the representation here of the hydrological processes may not be same or may not be as accurate as what this seems. Although the stream flow may be very much matching, the evapotranspiration may be completely different. So how do we get that, right? So how do we make sure that our process representation is as much as possible? So that's where we use these remote sensing techniques that provide a spatially and temporally consistent data of biophysical variables from local to global scales. Some of this data is at a very coarse resolution, some of it is at a finer resolution, right? But depending on the availability, we can use them if you are using a semi-distributed model or a distributed model to compare those aspects along with your stream flow, okay? Now coming to your products, you have soil moisture product, leaf area product, canopy cover, land cover, then you have the DEM. You also take soil data. Soil data is also now being extracted using remote sensing products, which are an input. In addition to that climate data, your precipitation, you have missions which can estimate precipitations from the satellite, right? So these products can be used as an input, and these products, some of these products can be used to evaluate your how good your model is, right? And one of the things that we say is, especially in data limited regions, although stream flow gauges give us a good indication, there are many missing stations, right? Our stream gauge network is still quite scarce, right? And on top of that, sometimes the gauge may malfunction. There will be many years of missing data, or there will be many months of missing data, right? So in those cases, your remote sensing products do help, okay? Anyone used any product, remote sensing product? Soil moisture, how many of you use soil moisture? 1, 2, 3, okay. ET, okay. LAI, okay, LAI, right. Okay. So some of these products are obviously can be used for other aspects, right? For example, Pawan is using for drought monitoring, yes. So in addition to that, it can be used for your ecohydrological modeling as well. Now what are the sources? You have NASA Earth observations, which is a repository which has the data that is available. Most of the data is freely available, and we use it for information of climate change, natural disasters, global ecosystems with tools for visualization and analysis. Okay, so NASA Earth observation is a good source of information where you can get raw and processed images. USGS Earth Explorer, from where we download a lot of data, right? So that is where you get the data from the satellites like Landsat, Sentinel, Aster, right? So users can search the data based on location data and sensor type. Again, most of the data is free, except for some part of the data. Then European Space Agency's Sentinel program, Sentinel data, that also has a Copernicus open access hub where you can get the Sentinel data, Sentinel program data, and which is used for Earth's environment, disaster management, and climate change research, right? Sentinel data is extensively used for soil moisture mapping. Yes, okay. Then NOAA class, that is also a hub where you can get the data. And in addition to that, we are, as a country, our data is also now becoming open access, right? Much of the ISRO's data through the Bhuvan portal or Bhunidhi portal, much of the data is getting open access except for certain resolution. I think anything above 10-meter resolution is becoming open access, yes? If it is less than 10 meter, you have to pay for it, right? But then you have NASA Earth data, which has MODIS, SMAP, and GPM missions, right? And MODIS has wide products. It has ET, it has LAI, it has different products, right? Which covers topics of oceanography, atmospheric science, and cryosphere. So these are some of the sources where you can get the data. Now, a new one, not new one, it is there for probably last 1-2 years, Google Earth Engine, or little before that, where it can extract the data from these particular sources, right? A simplified portal which can extract the data from all these sources and at the same time perform some of the GIS operations that are necessary to do before we can use it for any of the applications. Okay? So let's say you have a raw satellite data, a satellite image that has been taken. Anyone knows what all things needs to be done before it can be used? You need to do atmospheric corrections, then noise correction, geometric correction. What else? Radiometric correction. You need to do georeferencing. What else? Mask removal, cloud removal, yeah, shadows, you need to identify those, right? In addition to that, you may have to mosaic them. You need to stitch the images together for a large area, right? Even the image. And when we take a photo or when you take an image, the pixels will be varying, pixel size will be varying. As it goes to the edges, it starts increasing. But most of the data that you get is of a fixed pixel size. That comes from your corrections. Okay? So Google Earth Engine helps us in doing much of this using some simple codes or simple inbuilt functions that it has, and you can go and check it. It's not very hard. You can just go and learn it on your own, right? So it has it gives you for most of the open source data, and also the region of interest. If you give, it will extract the data for that particular region at a particular time, and you can also put some thresholds that I don't want an image which has more than 5% of cloud cover or 10% of cloud cover. So it will not take up that image, right? It has automated much of the processes which we were earlier doing using some of the GIS softwares or ERDAs. Okay? And you can do a lot of data analytics directly from there. You can take a finished product, you can do the analyze all the data. Some of the products are available, and you can even develop your own products in Google Earth Engine using this raw data. Okay? Anyway, if you go into Google Earth Engine, it in itself is a separate class, but then you can get it. Okay, now coming to your overview of remote sensing products, it started in 1972 with at least the Landsat 1, and over a period of time, you see here each bars indicate the data that it has. 1972, 1975, 1978, 82, 84. Landsat 7 in 99, but there was a failure in 2003, so there was some gap. Landsat 8 in 2013, and 2021 was your Landsat 9, right? Many of you would have used the Landsat imagery, yes? 8 and 7. Okay, so we have used these Landsat images. So that is the data that we get, and that is the data we process for our applications. Now, if you have in addition to Landsat mission, you have a MODIS mission. So Landsat with its missions of 1, 4, 5, 7, and 8 has a resolution of 30 meters, most of them, and a temporal resolution of 16 days. That is, every 16 days a image may come. So you sometimes it's not only one image per year, you need to have a temporal resolution. For example, if you are tracking a crop growth during a season, your crop is for, let's say, 120 days or 150 days, right? And if it's a longer crop, 180 or 200 days. Now, if you want to have a track of how the crop growth is happening, for some of the images, you need to have a high revisit time, right? Let's say every week, every 10 days, every 15 days, because in between the crop suddenly grows, and you want to capture that as much as possible. So the revisit time becomes important. Which product has what revisit time? Now your MODIS is also another mission, but it is at a coarser resolution. It's not at 30 meters, it is at 250 to 100 meters, right? But it gives you a lot of the products, right? Lot of this thing. The Sentinel ones, which are now are being used, vary in the resolution of 10 to 60 meters. It has both microwave remote sensing products as well as in the electromagnetic this spectral bands, 13 spectral bands, right? For a detailed monitoring of land cover, vegetation, frequent visit. It has a frequent revisit time of 5 days, but this data is available starting from 2017 or so, 2015 to 2017, right? 2015 is Sentinel-1, and then 17 is when your Sentinel-2 and other images have come. Okay, so you have different images. Sorry, you have different missions, different sensors. Now these sensors are at different wavelengths. They capture the data at different wavelengths. When we say that you are trying to capture the the reflectance of your electromagnetic radiation, we are trying to capture information at different wavelengths. Now different products or different surfaces will behave differently across different wavelengths. Okay? For example, if it's a green cover, there will be more reflectance in near infrared band, and that is where your vegetation indices have been developed. So similarly, based on the differences in these reflectance values across different wavelengths, you try to interrelate with our physical variables. Okay? In addition to that, different missions such as MODIS has these many bands, so it collects information in all these wavelengths. ASTER, it collects in these particular wavelengths, and you see, depending upon the wavelength, your spectral resolution is changing. Here it is 15 meters, here it is 30 meters, here it is 90 meters. So each sensor has a different resolution. Similarly, this is Landsat 7, Landsat 8, Sentinel-2 has a wide range, and each of them, this is around 60 meters, this is around 20 meters, and this is around 10 meters resolution, right? So depending upon the resolution, you have to have an understanding of what it is and where it can be used. Okay? So each, if you go into the specific of how a different product has to go, also you need to develop a relationship. You need to have a ground truth data, and then based on that, you need to identify a spectral signature. Now that spectral signature can be across different bands, or within a band, a time series, right? If it is a concrete surface, you expect across time it should be more or less same. The reflectance values should be more or less same, right? But it's a crop growth, across time it is going to vary, similar to with a forest, right? There may be some variations in some of the reflectance values. So to summarize that, you have different products, Landsat 1 to Landsat 9. These are the different bands. We started with green and red and near infrared, and over a period of time, more spectral bands started to getting added. And here is MODIS, which has almost 36 spectral bands, right? And even the aqua part and the terra part both have the 36 spectral bands. So different bands are used, and you have some signatures which are collected. It's not that everything is based on the ground truth. There are some stations located across the world to capture these signatures from the Earth's surface, right? There are instruments which do capture that to develop many of these products. So coming to your biophysical parameters, from these reflectance value, we try to develop what is the estimation of ecohydrological variables. It can be ET, it can be LAI, it can be what is the density of crop in terms of NDVI, right? So for ET, there are certain algorithms, that is Siebel surface energy balance algorithm for land and simplified surface energy balance. Okay. So, they utilize to calculate energy fluxes providing estimates of water losses from the land surface, right. So, in addition your precipitation missions, they try to see what is the density of cloud cover, and based on that density of cloud cover they estimate what is the precipitation. Okay. Now, one thing that we need to understand here is all of these are estimates. They may not be the actual values. Okay. They will be close to the actual values, but you just have understanding that is the estimated value. Okay. And then you have the soil moisture. We have many microwave remote sensing products which can estimate soil moisture at least to the top surface. Top 5 centimeters soil moisture is what we get from the satellite products. From that top 5 centimeter product, we try to estimate for deeper layers. Right? The different research is happening to develop a relationship between soil properties and what is the soil moisture content in the top 5 centimeter. Okay? And all these products are available to you, most of these products are available to you at a daily time step. But your satellite has a revisit time, which is minimum is 5 days, Sentinel. Landsat is 16 days. Any idea how we get daily information? You have used products, right? When you download this data, you have a daily information. We have a soil moisture of 0.25 degree of from ESA CCI starting from 1978 at a daily scale. It is? No. How is it becoming to daily values? You have taken an image, you can analyze it, you will get it at that particular instant, right? Whenever the satellite flows. Now, the satellite, when it moves in front of you, depending upon the timing, some days it will be morning 6 o'clock, some days it will be in the afternoon 3 o'clock, right? So, but how do you get the data throughout the year? Calibrating, yes, I mean to develop that you need to calibrate or you need to develop a relationship, yes.
One satellite is from north, it's kind of.
Even then you may get two different points, no? Multi-sensor is one of the ways. You have multi-sensor data where you develop a product using multiple sensors. So, one has a revisit time of 5 days, another one has a 10 days. So, whenever it revisits, you take that particular information from different bands. Any other method? We do use the data, right? Or we do integrate with land surface models. So, most of the products that you have on a daily scale is basically integrated or this data with a land surface model. Okay, land surface are your large scale models which can, this data can be integrated. So, there is a certain uncertainty in all that. So, I wanted to bring that point, right? You have the remote sensing product, it's not only from the satellite. So, when you use the MODIS or when you use the ESA CCI or SMAP soil moisture products, they are integrated with your land surface model, and those land surface model simulations is what we get. And mostly they are tuned so as to get similar performance, right? So, you have biophysical parameters which are important for understanding nutrient cycle, ecosystem productivity and modeling impacts of climate change on vegetation. So, you have ET, you have soil moisture, you have LAI, right? And in addition to that you can derive some more indices. So, these are the different products that are available for ET and soil moisture. You have MODIS ET which is at a resolution of 500 meters with a temporal resolution of 8 day. LXCET product which is at 5 kilometer by 5 kilometer daily this thing. GLEAM which is at 25 kilometer by 25 kilometer at a daily time step. Then from here you have ESA CCI, that is soil moisture from 25 kilometer by 25 kilometer, which is at a daily time step. Right? Then you have LAI data from MODIS, GLASS, and EUMETSAT, which are at different resolutions from 500 meter, 1 kilometer, 1.1 kilometer. Then you have precipitation, that is TRMM, CHIRPS, Persian, right? And then MODIS, which gives you the land surface temperature. Now my question to you is, MODIS ET has a resolution of 500 meters by 500 meters, which has a, what will be the area? Two lakh 50,000 square kilometers? 2 lakh or 25,000? No. 2 lakh 50,000 square kilometers. Right? Now, for 2 lakh 50,000 square kilometers, you are having square meters, sorry. Yeah, that's what I was thinking, there's something wrong. Okay. So 2 lakh 50,000 square meters, you have one single value of ET. Or if you want to take LAI, LAI is also same, right? Now within the 2 lakh 50,000 square meters, your ground conditions are going to vary. So how much valid is that LAI or ET value when you want to go back and compare, right? Probably it is applicable in a US or European catchment where the land holdings are large. You have a large area where a certain crop is growing. But for Indian conditions, we need to be careful while applying this data. It is possible that it may be completely misrepresenting, or at least how it is taking is something that we need to look. And similarly with your soil moisture, when you say 25 kilometer by 25 kilometer, it's huge. 25 kilometer by 25 kilometer is quite a large area. And then you have. So there are different downscaling techniques that have been developed to bring it to a much finer resolution, especially for the hydrological modeling. This coarser resolution helps us for many climate change studies, large scale studies. For large scale studies, these are good data. But when you are using it for a much smaller watershed, you have to be much more careful in applying them. You cannot apply them blindly assuming that everything is correct. Okay. Now coming to your remote sensing of vegetation, water interactions. As I said, the vegetation starts reflecting more in the near infrared band. This is your wavelength, this is your reflectance percentage value. And you see here in the near infrared band, you have a higher reflectance of vegetation, and soil is increasing into mid near infrared. So there are many indices. Two of the commonly used indices are NDVI, which is NIR minus red by NIR plus red. Okay. If it is close to 1, that means a dense healthy vegetation. Close to 0 means its vegetation is less. At the same time, you have enhanced vegetation index, which also accounts for atmospheric conditions and ranges between -1 to +1, which considers NIR red and as well as the blue band. Okay. Similar to your vegetation indices, there are water indices also. Right. So there are NWI. So these water indices are also used to extract what are the water bodies from this particular, and lot of research has been done, lot of work has happened in that line. So how do we integrate? Now let's say you have the product for your area, you have developed a product, you have raw data from the 30-meter resolution, you have developed your LAI, ET for Indian condition. So how do we integrate that in the eco-hydrological models? Anyone? You have an eco-hydrological model which is simulating all the water balance components. You have stream flow, measured stream flow. On top of that, you have remote sensing product as well. Let's say ET, soil moisture, LAI, something. Now, how do I use this information to improve my model? One is data assimilation, and anywhere else? Yes, you can see whether your spatial representation in your model is matching with whatever you are getting from your remote sensing products. To check whether my process representation across space is correct or not, right? And another aspect is obviously you calibrate your parameters by considering them. Instead of just stream flow, you bring it into your model and try to constrain your calibration to have a better aspect, right? So that is what. So the spatial data of eco-hydrological variables can be utilized to improve the spatial representation of hydrological process and vegetation dynamics within the model. You can improve your vegetation dynamics as well, your crop growth, your forest growth. And then the integration of remote sensing models can be achieved through data simulation, right? In data simulation, the states of the models are updated. Compared to calibration, there's a difference in data simulation. Your states are updated. For example, if you have the soil moisture information on a particular day, in your water balance computation, you know your calculated value is X and your observed value is X dash. So it merges these two information. It updates this soil moisture from X to X dash, and in that process, it also adjusts other variables of your water balance. It's not only that particular parameter. It has to adjust all other parameters, all other variables to adjust to maintain the water balance. Okay? And also you have try to minimize the error between the simulated and observed variables, and also you can estimate the model parameters for calibrating. Okay? Usually you can use it in combination with stream flow, but in some cases where stream flow is not available, some locations they are also used individually, okay, for the ungauged basins. So data assimilation techniques, there are different data assimilation techniques. One is Kalman filter, ensemble Kalman filter, which tries to do it on a recursive basis, continuously updating the predictions and new observations as they are received, and it considers the uncertainty in your observation as well as uncertainty in your simulations. Okay? So it combines the model's predicted states with new observational data to produce an optimized estimate that reflect both sources of information. Okay? And this approach effectively minimizes the errors and enhances the model's accuracy over time, right? On every particular day, whenever the information is there, it keeps on updating that. So, ensemble Kalman filter is a upgradation of your Kalman filter, which employs a statistical ensemble of model states rather than a single estimate. So, Kalman filter uses a single estimate, whereas ensemble uses a range of values, right? And it is more useful in nonlinear systems such as hydrological system or eco-hydrological systems. They are not really linear. So, in those cases, your ensemble Kalman filters are quite reliable in assimilating the data. Okay? So, it is you have the hydrological model, you have the SMOS, observations, GRACE data. You use the ensemble Kalman filter for assimilation. It gets incorporated here, and it improves the model's output and validation. Right? Surface soil moisture and groundwater levels are given as a assimilation part to the hydrological models. Okay? So there are many studies which have come out of it. If you are really interested, if it's relevant to your work, you can go back and read to them. Model calibration. As when I started that you assume the stream flow to represent the changes in your catchment characteristics, and that is where we calibrate with the stream flow. And mostly we try to minimize the error between observed and simulated stream flow. Right? We try to minimize the error between observed and in that process, sometimes we have unrealistic parameters. We may have a parameter which may be completely different from what is there in the actual, right? And that is that stream flow measurements are point data, and calibrating with only point data at the catchment scale does not guarantee that spatially varying water balance components are simulated accurately. Various studies have shown this, that although the stream flow measurements may be good, but it does not guarantee that spatially varying water balance components are simulated accurately. Now, when we are talking about eco-hydrological modeling, this is something we have been saying starting from the starting, that you are using eco-hydrological modeling for something other than just estimating the stream flow. You are interested in process representation. You are interested in something other than stream flow as well. While stream flow is important, in addition to that, you are also interested in some other variable of your interest. So in such case, if that process is not getting simulated properly, then whatever analysis that you do may not be appropriate. Okay? So it is assumed that the point-based measurement represents the entire watershed response to the changes, and parameters are estimated based on this response, right? And while this approach has led to satisfactory performance, I'm not saying that it's all bad. It is still a good method, but the spatial representation of a hydrological process may not be accurate. We need to go back and check whether our other processes are simulating well, right? And we always use streamflow data because of absence of in situ measurements, right? Now that if we have a remote sensing product of LAI or ET or soil moisture, we can use them to calibrate the hydrological model, right, in the calibration process. So where you have a model, you take the observations, you compare them, right? It can be a single objective, it can be a multiple objective, multivariable optimization. We have a case study where we are talking about this, right? And then you try to improve this, okay? And in that process, your entire simulation may improve, and that may or may not get reflected in your streamflow simulation. How many of you have heard about the term equifinality? Equifinality. What is equifinality?
Different sets of inputs. You get a similar response.
Okay. How do you bring it to the calibration part?
When we sample the parameters on a basis, for different combination of the parameters, we get an improved result. For the indices, so which may, say for example, for a minimum value of a parameter, we may get a maximum value. So we don't have a good idea to choose which is the best.
Yeah. So when you do calibration process, and now most of us are doing an automatic calibration process, your optimizer will give you different combination of parameters giving similar result, or in some cases same result, right? So if you go back to your ESCO and EPCO values, let's say a performance of 0.8 or 80% accuracy can be obtained with a ESCO of 0.5 and a ESCO of 0.8 or 0.9. Now in both the cases, your water extraction from different soil layers is different, but you are getting a similar accuracy. Now your combination of parameters may lead to a same solution, right? And that is what is your equifinality problem. So it goes back to what Professor Chaubey was telling. You are getting the right results for the wrong reasons, right? The simulation is, the stream flow accuracy is good, but your simulation is wrong, okay? So to address that, probably we can incorporate, one of the hypotheses is, if you incorporate some of these spatial variables, we may be able to reduce that equifinality problem. We may be able to reduce the uncertainty in your parameters problem, right, up to a certain extent, okay? Various people have tried it. It is going on from almost last 7-8 years. A lot of research has come out, and it's still coming out, okay? And one of the case study that we are going to refer to is of Rajiv et al. 2018, a Journal of Hydrology paper with the title Hydrological Model Predictability Improves with Spatially Explicit Calibration using remotely sensed evapotranspiration and biophysical parameters, right? So nice paper, you can go ahead and read it, okay? The information that is contained in stream flow may not be sufficient, so they say, to capture the vertical fluxes, the water fluxes, the movement of water in the vertical direction at different spatial and temporal scales. So what they hypothesized is that using spatially available water balance components in multi-objective calibration may improve the equifinality issue, right? They may have, we may be able to address this particular issue. So they used different calibration strategies. We'll talk about it. They considered the biophysical parameters also in the calibration. At the same time, they considered the spatially available ET in addition to the stream flow, right? They used the MODIS ET data for their particular catchment, okay? So they hypothesized that although the simulations may be better, the stream flow may be more or less. So they were not saying that we will improve the stream flow simulations. If you see the hypothesis, they said they may improve the equifinality issue. That is, You will try to have the right results for the right reasons. Okay? So they did it for a catchment here, which is quite big with lot of agricultural area and lot of water bodies. And then this is the ET map, modest 8-day local ET map that you have. And one of the things they did in this study, which I'm not going in depth, is they modified the SWAT code. They modified the SWAT to incorporate these small water bodies. They updated the SWAT code to make it flow through these small water bodies so that it gets simulated well. So they use 4 calibration strategies. The first, which is the baseline calibration using streamflow data. M2 is you use the calibration, but in addition to the streamflow parameters, you consider biophysical parameters as well. It is your crop growth parameters. Then the third one is M2, where you consider the streamflow and biophysical parameters. They used lumped DT, that is, they lumped the evapotranspiration using weighted area average method to the calibration. And M4 is they did same as M3, but for individual subbasins separately. They did it a spatially discretized approach for optimization. So basically, you are increasing the complexity. Number of parameters here were 21, that became 31. Then you added another variable, so your optimization complexity kept on increasing. And here M3 was having a single ET value for the entire watershed, where M4 was individual subbasins had one ET value. Okay? So to describe, you have a modified SWAT, you had streamflow with 21 parameters, and then the second case where you had 31 by adding 10 biophysical parameters, only streamflow, which was considered to be baseline. Then you have streamflow with 31 parameters, M2, streamflow with lumped actuality, M3, and streamflow with spatially distributed actuality as M4. These are the parameters. These are your streamflow parameters for surface and subsurface, channel routing, and snow accumulation. Snow-fed catchment, you need to consider snow accumulation, snow parameters. In most of the Indian catchment, except for the northern part, you will not have the snow, at least in the peninsular catchments. You don't need to consider them. But these are some of the streamflow parameters that they considered. They also did the sensitivity analysis to find out which parameters were sensitive. So this was for the M1 case. This was followed by considering the biophysical parameters. These parameters we have seen yesterday, remember? In the database. Yes? BLAI, maximum potential leaf area index. DLAI, fraction of growing season when leaf area declines. LI max, first point on the leaf area development curve. So on and so forth. Maximum rooting depth, maximum canopy height, fraction of stomatal conductance, vapor pressure deficit, and radiation use efficiency. Okay? So these are some of the 10 parameters which they also included in the streamflow simulation. When you are doing with streamflow, just having a streamflow, they used KGE, Kling-Gupta efficiency, and estimated or included these also in the calibration process. So basically, this will change your other water balance components such as ET and other stuff. Okay? So let's see the results. Let's first see the streamflow simulations. Hardly any difference in any of the configurations. It says 0.91, 0.91, 0.92, 0.9. There is some difference in the validation period, but in general, if you see, the streamflow simulation is more or less consistent. But what happens to your subbasin level accuracy in ET simulations? Your ET simulations are changing here. This is color coded for KG score, starting from yellow from 0.4 to blue of 0.75. Now this is M1, where you're simulating with only streamflow alone. And you see here, there are many basins in yellow and green, which indicate a score of less than 0.5. Now when you go to M2, where you are incorporating the biophysical parameters, there is an improvement. The KGE scores for ET are increasing. Now that further increases when you are taking the lumped ET, M3, right? More of the basins, subbasins are now into the 0.6, 0.65 above. And that further improves when you are considering a spatial discretization. Now, in this multivariable, multi-objective, they took the Euclidean distance and weighted average method to get it. But then, in general, as the more complexity increased, it has a better representation of ET. That means our biophysical variables or other ecohydrological variables are probably getting simulated better. The crop growth is getting simulated much better than what was happening here alone, right? So, it is, if you look at just stream flow, it is still 0.9. Validation, it is increasing to 0.75 because your water balance components are probably increasing, okay, and that actually helped. Okay. Now, what happens to your stream flow? Your 0.9, what you have seen is the average for the entire watershed, right? But if you discretize them into high, medium and low flows, the black line is your observed, blue is your M4, that is the fourth one, this one which is considering your ET and stream flow spatially discretized, and M1 and the gray one is the M1. In the high flow, as you can see here, compared to the USGS, your M4 is closer, and that close association increases in your medium and low flows. So, your low flows and medium flows were started to getting simulated much better, because probably the soil moisture simulations improved with the crop growth. So, once the soil moisture simulation starts getting improved, it affects your lateral flow, it affects your groundwater recharge, and it affects your base flow conditions, and that is where your medium and low flows were getting improved, right? And coming to the uncertainty, when we say that we are reducing the equifinality, this is M1 and M4, this is a relative difference in uncertainty in water yield production. The lighter colors, that is the blue, indicates low and the red indicates large. So, as you can see here, from compared to M1, the uncertainty has reduced. That is also available in your stream flow hydrograph. So, if you have the uncertainty band, M1 is quite large as compared to M4. So, M4 band has also decreased, right. So, this is something which was fascinating, and this is something which we also tried for the ungauged basins. We have not tried with the SWAT model, but we used a conceptual model GR4J to see if we can predict the parameters or estimate the parameters using soil moisture data alone. One of the study which Pattabhiraman had done while being here, it took different catchments, and this was basically ungauged study. You have the ungauged catchments, and to estimate the ungauged catchments, estimate the parameters of ungauged catchments, one of the ways was the regionalization approach. Okay. In that approach, you take the similar catchments, estimate the parameters there, and then transfer them to the ungauged location, right. Now, that is the traditional approach, but it also had a lot of uncertainty. So, we wanted to look at, can we reduce that uncertainty by adding the soil moisture data in the parameter estimation approach. Now, what we observed was our uncertainty reduced something like this, but the accuracy was more or less similar, right. We had the almost similar accuracy as just using regionalization technique, right. So, which has an application, but at the same time you also need to understand that many of these are estimates. Don't take them as absolute truths, similar to what you take for your models. You need to understand what is the process, what is the uncertainty, and based on that make your inferences or conclusions. Okay. So, to summarize, we have remote sensing that provides consistent spatial and temporal data for variables such as ET, soil moisture, in some cases water quality as well, improving eco-hydrological models, especially in data limited regions. We have large scope satellite data from Landsat, MODIS and Sentinel, along with machine learning algorithms, enhances the extraction of eco-hydrological variables, and vegetation health, improving large scale modeling. You can use data assimilation techniques such as Kalman filters and ensemble Kalman filter to update the model states with remote sensing data, reducing errors and improving predictions in complex systems. At the same time, you can also use calibration, like what the case study we have mentioned, to improve the spatial accuracy through uncertainties in the data needs to be considered, right. So, final take home message is remote sensing data is there, remote sensing products are available. Use it, but use it with an understanding. Everything, if you are trying to do a eco-hydrological model, you are trying to have a physical understanding of the system. So the physical processes must be represented as accurately as possible. Don't take just any data, apply it and say, this is what I got. You try to see whether the data that you are taking, if it reflects the physical variables or not, right? So that uncertainties in the data also must be considered. Okay, questions? Yes.